4 engines became the standard for safety. Then, Boeing bet everything on 2. But here's what nobody tells you about the 737. It had been a regional jet that now crosses oceans. Nearly 60 years of continuous production, over 12,000 delivered, the second best-selling airliner in history. What happens when you refuse to start over? When every improvement must fit within a framework designed before the moon landing. You get engines flattened like pancakes, landing gear that never fully retracts, technology borrowed from propeller planes, and a hubcap that can ground a $100 million jet. Each quirk tells a story about engineers who made impossible things work, about airlines that refused to let it die, about an aircraft that was supposed to be temporary but became immortal. Today, you're about to discover why this design still dominates the skies, from desperate engineering solutions to grandfather clauses that bend modern regulations, from built-in stairs that somehow still make sense to backup systems from another era. And the first quirk? You can see it every single time you board. Quirk 1. The flattened engine solution. The 737's engines have flat bottoms. This isn't aerodynamics, it's desperation. Boeing designed the original 737 low to the ground. Baggage handlers needed to reach cargo holds without ladders. Passengers could board via built-in stairs. Ground clearance drove everything. The original Pratt & Whitney JT8D engines fit perfectly. Compact, round, problem solved. Then, airlines demanded efficiency. Boeing responded with bigger CFM56 engines on the 737 Classic. These new turbofans promised massive fuel savings. They didn't fit. So, they did something radical. They flattened the bottom of the engine nacelle, took a circular tube and squashed it until the underside was flat. Your multi-million-dollar turbofan literally reshaped to fit under a wing designed in the 1960s. The flat bottom creates slightly less ideal airflow, but efficiency gains from the larger engine more than compensate. Airlines save millions in fuel, but this compromise created a cascade. The 737 MAX needed even bigger CFM International LEAP 1B engines. Boeing pushed this solution further. Engines so large and so forward, they changed the aircraft's pitch characteristics. That led to MCAS, which led to 2 crashes, which grounded the entire fleet worldwide, all because an early decision to sit close to the ground created a domino effect lasting 6 decades. The best engineering solutions are often the ugly ones that actually work, until they don't. But if you think flattened engines are unusual, wait until you see what happens to the landing gear. Quirk 2. The naked landing gear. The wheels don't disappear when the gear retracts. You can see them. No doors, no covers, just rubber and wheel hubs. Almost every modern airliner tucks its gear behind closed doors. Clean, aerodynamic. The 737 flies with its wheels visible under the fuselage. This isn't an oversight. It's vintage Boeing philosophy. Simplicity over sophistication. Landing gear doors add weight, complexity, potential failure points. Boeing made a choice, skipped the doors entirely. Instead, it used blade seals, rubber flaps that form around the wheels, and oversized hubcaps that complete the aerodynamic profile. Not elegant, but functional. Here's where it gets interesting. Those hubcaps aren't optional cosmetics, they are mandatory safety equipment. Each one contains wheel speed sensors that feed the anti-skid brake system. Lose a hubcap and you've lost critical safety data. More on that later. Modern 737s still use this exact system. Why? Boeing's type certificate is grandfathered from 1967. Changing to enclosed gear bays would require massive recertification, billions in costs, years of testing. The crude solution from decades ago remains good enough for 2025. Every time a 737 retracts its gear, you're watching a design decision from the Johnson administration. Quirk 3. Stairs in your pocket. The 737 is the only modern mainline airliner with built-in stairs. While Airbus jets and Boeing's larger aircraft require jet bridges or mobile stairs, many 737s carry their own staircase, tucked under the forward door, ready to deploy in seconds. Passengers board from the front, disembark from the rear, no ground equipment needed. Ryanair uses this for their sub-30-minute turnarounds. The irony? This, now optional feature, exists because the 737 was designed for regional airports lacking infrastructure, small towns, places where jet bridges didn't exist. Today, the 737 serves London Heathrow, New York JFK, and Singapore Changi, airports with state-of-the-art jet bridges on every gate. And yet, that built-in staircase remains an option. Low-cost carriers discovered it's faster and cheaper than waiting for airport equipment. Ryanair will park at a gate with a perfectly functional jet bridge and deploy the aircraft stairs instead. The feature weighs around 200 pounds. That's fuel you're carrying every flight. Most airlines remove them, but for carriers obsessed with quick turns, those stairs are worth their weight in gold. Boeing has been delivering brand new 737 MAXs with built-in stairs for customers who opt for them in 2025 for airlines flying to airports with billion-dollar terminals. Sometimes the best technology refuses to die, but the stairs aren't the only backwards feature. Quirk 4. The backwards cargo door. Most aircraft cargo doors open outward. Swing them out, load the cargo, close them up. The 737's cargo doors open inward. In 2022, a KLM 737 landed in Amsterdam with its forward cargo door partially open. Passengers filmed a gaping hole in the fuselage as the jet taxied. Nothing fell out. No bags, no cargo. Everything stayed put. Why? Because 737 cargo doors are pressure-actuated safety features. When the cabin pressurizes, thousands of pounds of internal pressure push outward on every surface. On most jets, this requires robust locking mechanisms on outward opening doors. If those locks fail, the door can blow out catastrophically. The 737's inward opening doors use cabin pressure as an additional lock. Even if mechanical locks fail, pressure physically holds the door shut. The door literally cannot open during pressurized flight. It can only open when pressure drops, like after landing. In that KLM incident, the door locks had failed before takeoff. Cabin pressure kept it sealed during flight. Only when the aircraft descended and pressure equalized did wind forces push the unsealed door inward. The downside? Cargo loaders can't maximize space. That inward swing takes up room. But for safety? Brilliant. A vintage solution that turns physics into a backup system. Boeing never advertises this. Most passengers have no idea. But it's one reason cargo door failures on 737s have never caused a catastrophic in-flight event. The best safety systems are the ones you never think about. Quirk 5. The low-tech memory aid. The 737 pilot's yoke has 3 rotating number wheels. They look like something from a 1940s submarine, completely mechanical, no electronics. It's a trip indicator. Pilots still use them. A crew can fly 6 different flight numbers in a single day. Newark to Chicago, Chicago to Denver, Denver to Phoenix. By afternoon, it's surprisingly easy to blank which flight you're currently operating. When ATC calls, you need to respond instantly. United 2847, turn left heading 270. That split second of hesitation could create confusion. So, pilots set those 3 wheels to their current flight number. Always there, always visible, no scrolling through menus. Modern aircraft display flight numbers on glass screens, but screens can fail. Screens can be cycled to different pages. Screens require power. Those 3 wheels, they work whether the aircraft has power or not. Visible in peripheral vision, never need updating or rebooting. Boeing included this feature from day one and never removed it. 737-100 all the way to the 737 MAX, over half a century of continuous service. In an era of touchscreens and artificial intelligence, the 737 cockpit includes a device that wouldn't look out of place on a World War II bomber, and it works better than any app ever could. But here's where things get really old school. Quirk 6, the jet that thinks it's a Cessna. The 737 is one of the last jets in production that you can fly with your bare hands, like a Cessna or a DC-3. Losing hydraulics usually means you're having a very bad day. Even then, you can still fly the 737. Barely. The 737 has manual reversion capability. If every hydraulic system fails, pilots can control the elevator and ailerons using pure muscle power through mechanical cables. Control cables run from the yoke through the aircraft to the flight control surfaces. Normally, those cables input to hydraulic actuators that do the heavy lifting, but hidden in the linkage are locking mechanisms. When hydraulics fail, those mechanisms unlock. The cables connect directly to small tabs on the control surfaces. Moving the yoke pulls the cables, which pulls the tabs, which create aerodynamic forces. It requires incredible force, but it works just enough to keep the aircraft controllable. Why does the 737 still have this technology? Because Boeing designed it when hydraulic reliability wasn't proven. Manual reversion was the ultimate backup, and removing it would require massive recertification. So it stays. This ancient, rarely used system of cables, pulleys, and mechanisms threads through the entire aircraft. Every other modern jet would be unflyable in the same scenario. Sometimes paranoia from decades ago saves lives in the 2020s. And speaking of unexpected safety systems, Quirk 7, the critical hubcap. Remember those exposed main wheels with oversized hubcaps? On a 737, losing a hubcap can ground the aircraft. Not because it looks bad, because it's a critical safety component. Inside each hubcap is a wheel speed sensor. As the wheel spins, the sensor generates electrical signals proportional to rotation speed. That data feeds the anti-skid brake system. The anti-skid system needs to know exactly how fast each wheel is turning. When you land and hit the brakes, if a wheel starts to skid, the system reduces brake pressure to that wheel. No wheel speed data, no anti-skid protection. Regulations forbid operating a 737 without functioning anti-skid. It's mandatory. So, if a hubcap falls off during taxi, the aircraft cannot depart. Ground ops has to find the missing hubcap or install a replacement. Boeing could have mounted those sensors elsewhere, inside the wheel well, on the axle, anywhere protected, but they didn't. Because in the 1960s, the solution was integrating the sensor into the aerodynamic hubcap. Two birds, one stone. 60 years later, the 737 MAX uses nearly identical hubcaps with integrated speed sensors. It works. Compare that to a hidden sensor failure that might go undetected until you're stopping on a wet runway. The 737's wheel hubcaps are flight-critical components. Quirk 8. Pitot tubes in unlikely places. Most aircraft have pitot tubes on the nose, measure airspeed where the air is cleanest. The 737 has pitot tubes on the nose too, but it also has two more in an odd location, on the vertical stabilizer. Why measure airspeed back there? You're not. Those aren't for pilots. They're for the elevator fuel system. The 737's elevators are hydraulically powered. Without artificial feel, the control column would move with zero resistance. Pilots wouldn't know how much force they're applying. So, Boeing installed an elevator feel and centering unit. This computer calculates how much resistance the yoke should have based on airspeed and stabilizer position. Flying fast, heavy control forces. Flying slow, lighter forces. But using the nose pitot tubes would give false readings during high angle of attack situations, like takeoff or landing. The nose is pointed up and the pitot tube isn't facing clean air. Solution: mount dedicated pitot tubes on the vertical stabilizer, where airflow stays consistent, regardless of aircraft altitude. Those tail pitot tubes feed data exclusively to the field computer. They exist solely to make the yoke feel right. It's invisible sophistication, a system working perfectly that pilots never think about. Until it fails. Then the control forces feel wrong. Too light at high speed, too heavy at low speed. Most passengers walk past the tail, board the aircraft, and never notice the small probes on the vertical stabilizer. But without them, flying a 737 would feel like steering a video game, artificially light, dangerously disconnected. Quirk 9. The winglet evolution. The 737's wingtips showed decades of evolution. Early 737s had none, just flat wingtips, efficient enough for their era. Then came blended winglets in the 2000s, curved upward tips that reduced drag and saved fuel. Airlines loved them. But aviation partners Boeing didn't stop there. They invented split scimitar winglets, adding a second, downward-facing tip below the main winglet. The result? An additional 2% fuel savings on top of already efficient blended winglets. Do the math across a fleet, and you're talking hundreds of millions in annual savings. Here's what's brilliant. These winglets are retrofittable. You don't need a new aircraft. Aviation partners Boeing will unbolt your old winglets and bolt on the new split scimitars. Older 737NGs can upgrade. It takes days, not years, and the fuel savings pay for installation in 2 to 3 years. The 737 MAX took it further with advanced technology winglets, Boeing's optimized split-tip design with advanced coatings that encourage laminar airflow, blended and scimitar, now retro-only. Why does this matter? Because the 737's design is so old, Boeing's been forced to squeeze efficiency from every possible angle. They can't redesign the fuselage or wing, those are locked in from decades ago. But wingtips? Those can evolve. While the core 737 airframe is nearly 60 years old, the wingtips represent cutting-edge 2020s aerodynamics. Walk through any major airport and place spot the winglet. Blended, split scimitar, max winglets. Each represents a different era, all on fundamentally the same wing. You don't always need a clean sheet design. Sometimes you just need to keep improving what already works. But there's one more quirk that ties everything together. Quirk 10, the grandfather clause. The 737 doesn't have to meet modern regulations. It's grandfathered in. When Boeing designed the 737 in the 1960s, it met all safety requirements of that era. And as it stretched, upgraded, and modernized the 737 over 6 decades, it never had to fully recertify to current standards. The exposed landing gear would never be approved on a new design today. The low ground clearance forcing flat engines, modern regulations would demand different solutions. Even the manual reversion system uses technology considered obsolete. But Boeing doesn't have to change any of it. They only need to meet the 1960s standards for the core type certificate. This is why the 737 can keep evolving without becoming a completely new aircraft. Change too much, and you'd need full recertification under modern rules, a process costing billions and taking years. So, Boeing walked a tightrope, upgraded the engines, improved the winglets, modernized the avionics, but kept the fundamental airframe, landing gear, and flight control architecture unchanged. The 737 MAX pushed this to the absolute limit. Those massive LEAP engines changed the aircraft's handling characteristics, enough that Boeing needed MCAS to mask the difference, because admitting it flew differently would mean requiring new type ratings for pilots, breaking the "it's still just a 737" promise. We know how that turned out. The grandfather clause is both the 737's greatest strength and its Achilles heel. It allows continuous improvement without starting from scratch, but it also locks Boeing into design decisions from an era when computers filled entire rooms and fuel cost pennies per gallon. Every quirk we've discussed traces back to this reality. The 737 is an aircraft from another era, wearing a modern costume, and somehow it still flies. The 737 was supposed to be retired decades ago. Boeing planned to replace it with the 757 in the 1980s, then maybe a clean sheet design in the 2000s. None of it happened. Why? Because airlines didn't want a replacement. They wanted more 737s. The efficiency of keeping pilots on one type rating, the common fleet benefits, the proven reliability of an airframe refined for 60 years, the economics were unbeatable. So, Boeing kept building and upgrading and stretching. The 737-100 seated 85 passengers in a 2-class configuration and flew around 1,500 nautical miles. The 737 MAX 10 seats up to 204 passengers in a 2-class configuration and flies around 3,100 nautical miles. That's not evolution, that's transformation. Today, the 737 remains one of the most in-demand commercial aircraft, with thousands on order and production booked years into the future. And here's what's fascinating. In an industry obsessed with the latest technology, the most successful aircraft is the one that refuses to be new. It takes pragmatism from another era and incrementally improves it year after year. No revolutionary materials, no radical aerodynamics, no game-changing propulsion. Just relentless, unglamorous refinement. The 737 will likely still be in production in 2030, maybe 2040, over 70 years of continuous manufacturing. No other airliner comes close, because sometimes the best technology isn't the newest, it's the one that works, that airlines understand, and that refuses to die. Hey, before you go, the YouTube algorithm thinks you're going to like this video next, so why not check it out?